As mentioned, my name is Braeton Smith, Argonne National Lab. Most of my work focuses on critical material supply chains, but I come at it from slightly different perspectives as an economist. We're trying to look at the whole system kind of holistically. So I'll cover some of what was talked about earlier, at a much higher level, since I'm not a metallization expert or metallurgist or anything like that. But planning to cover basically the market for rare earth elements and permanent magnets, followed by some discussion about how we think about the supply chain, different parts of the supply chain, where things are occurring, general material criticality, how rare earths play into that, and the supply chain vulnerability associated with rare earths, but also so first, we're talking about magnets. Magnets are all over the place. They are in pretty much any microelectronics, commercial electronics, industrial electronics, really useful for making things smaller and more efficient. When we're talking about the energy, especially the energy sector, industrial base, we really care about them as far as wind turbines go, especially for offshore wind turbines and for electric vehicles. They allow us basically to make really large wind turbines that are more efficient. They can produce these like 15 gigawatt type size wind turbines offshore. They require less maintenance. They just are overall larger, more efficient, or require fewer moving parts. Same with vehicles. It allows you to make a lighter weight vehicle, which means you can have more power from your battery. You can have a bigger battery. They can go farther. Whole kind of system working together. If you use heavier magnets, more strain on your battery, less efficient vehicle, etc. Specifically, when we're talking about magnets in the context of rare earth magnets and in these technologies, we're talking about neodymium iron boron magnets. There's another type of rare earth magnet called samarium cobalt, which has more applications in things like sensors and really high temperature applications where you don't need necessarily as much power. But if you need those high power applications, you need the neodymium. There are other permanent magnet types that don't use any rare earth elements, such as ferrites, things like that. I won't talk too much about those today. But as I mentioned, within the energy sector industrial base, there's a really strong preference for specifically what we'll call sintered neodymium magnets. These are basically magnets that are stronger, they're less brittle. I think Ron's probably going to talk more about that later, how we make magnets. So a lot of you have probably seen this figure before. This is why we care about rare earth elements. And this all started back in 2010 when China decided to decrease their export quota for rare earths because of some trade dispute with Japan. And everybody freaked out. The prices of some of the elements, especially what I show here, dysprosium, increased by over 2,000% in a matter of like 6 months. All of a sudden, everybody became very concerned about where are we going to get these materials? What do we use them in? How is this going to affect our climate goals? How are we going to put these into our defense systems, our jets and whatnot? So this figure right here is basically why CMI exists. We don't want to prevent this from happening again. And so this spurred a lot of attention and investment in rare earth elements, in magnet technologies, developing substitute technologies, a lot of the things that CMI is focused on today. So we talked about demand for rare earths. So back in 2020, we did this supply chain report, which I forgot to mention. This a lot of what I'm going to talk about today is from this rare earth permanent magnet report here that was published in 2022, which was funded by the DOE Office of Policy, which was really trying to look at the vulnerabilities associated with the magnet supply chain. So a lot of the content I'm going to present is out of that report and covers basically our overall assessment of what was making that move. So back to demand. You can see by 2030, under aggressive decarbonization scenarios, which we were assuming a net zero economy by 2050, which is very aggressive. But in order to do this, demand for electric vehicles and demand for offshore turbines was going to grow exponentially. So you can see that the demand for sintered neodymium magnets over that 10-year period is going to definitely more than double. And by 2050, I guess that's like growth by 5 times. And then how does that translate into growth for neodymium, praseodymium, and dysprosium, which are used in these magnets? It's all based on grades, which I'll talk about later. But you can see there's like a threefold increase in demand for all these products over time. How does this demand relate to what we actually produce in the US to actually meet these goals? Currently, what we're showing in the gray chart here is just the supply of rare earths from the US and Australia, which is currently rare earths that come from US and friendly countries. How that translates into actual production of rare earth oxides, supply and demand for rare metals and alloys, specifically we're talking about dysprosium and neodymium here, and then how that goes into end uses. And so you can see that really this is being driven by offshore wind turbines, electric vehicles, and industrial motors as we move forward. And then widespread use in consumer electronics as well. Now I'd like about the supply chain. So I heard a lot this morning about the first stage here, raw materials production. We talked about rare earths and magnets. We really divide it into these four categories: raw materials production, process materials, magnet manufacturing, component final product manufacturing, and then end of life. So raw materials production includes everything that Rock was talking about this morning as far as primary sources go. So your bastnasites, monazites, ionic clays, all those things fall under the raw materials production, and all the way through basically your concentration technologies that Lana was talking about as well. Unconventional sources, which include things like coal ash, geothermal fluids, mine tailings from previous deposits that are currently unexplored. So maybe there's a lot of rare earths in those. And then secondary sources, which are recycled products. So secondary sources really tie back into the end of life step over there, where you're talking about recycling hard drives, MRI machines, where they use a lot of magnets for their processes. Process materials production, we get into, this is rare earth separation. So anything, when you go from your rare earth concentrate, you have to separate it into individual oxides so that those can be used for their various downstream applications, especially that includes magnets. So separation from a rare earth concentrate into neodymium oxide, dysprosium oxide, didymium oxide, which is an alloy of neodymium and praseodymium. And then you have to refine those into metal as well. So actually production of these metals goes into our process materials production. And you take those metals, make them into an alloy, your magnet manufacturing. Which I won't talk about too much, the steps involved in that. I think there's later presentations on that as well. But then you actually make the magnet, and then those go into your subcomponents and then your final uses. So your subcomponent would be like a direct drive generator that goes into the wind turbine. So there's a company that makes the generator, a company that may sell for the wind turbine, and then a company that assembles the actual wind turbine. Similar for electric vehicles. And then end of life would include anything that involves recovering the end of life products, actually dismantling them, shredding them, recovering the material, and basically starting over from the process materials production. Walking through each of these steps in a little more detail. We had a lot of information this morning on rare earth elements, so I won't go too much into detail, but basically rare earths are chemically similar. They happen to occur in similar deposits around the world. As I heard this morning, chemically difficult to separate, a lot of very difficult, very specific extractive processes, and often they're co-products of one another, which makes them complicated when you're trying to sell them on the open market, because you're not just extracting one thing, you're extracting a slew of probably 10 different things that you're trying to sell, and some of them you can't sell. So that adds a lot of difficulty to the process. Specifically, we mentioned that neodymium magnets rely on rare earths, neodymium, praseodymium, and dysprosium, which are two light rare earth elements. So we have praseodymium and neodymium. I think Lana talked a lot about that. Light rare earth elements, and then the heavy rare earth elements, dysprosium and terbium, which help you increase your gross survey, which means it operates at higher temperatures. Production of rare earth elements in the raw material stage is really dominated by China, though it used to be prior to 2010, when we had that big price spike, it was about 95% dominated by China. Since then, other players have come on board, specifically the Mount Weld mine in Australia and the Mountain Pass mine in California. So now China produces about 58% of all the initial raw materials production. US, I think, produces about 22%, something like that. So this is getting a little better in terms of the actual raw material production stage. And then as far as other materials going into magnets, of course, it's not just the rare earth components that we care about. We also care about the boron going in, the iron, some of the nickel that goes into the plating, things that are often kind of overlooked when we're talking about magnets. But of course, the rare earths really drive most of the conversation because they're the hardest ones to get. But as these maps clearly show, as we move further into the separation and refining stages, things get a little more tricky. So once we go from about 58% of the market being controlled by China for their actual raw materials production, separation is closer to 90%, metal refining closer to like 95%. So they still pretty much dominate everything from the outside of the raw materials production stages. And even so, there's silver refining outside of China as well, but you can see it's largely concentrated still in that Southeast Asia part of the world. There's some production in the UK and Estonia, but it's pretty small relative to these materials. So as I mentioned before, different uses require different types of magnets, and that's true even within the space of rare earth magnets. Uses we usually talk about require sintered magnets as opposed to bonded. Sintered magnets are stronger, physically stronger, they're less brittle as a breakage, and they're also more powerful. So your more powerful applications require the sintered magnets, and they require different grades. So different grades of neo, they can have more flux, which means they're just stronger. They can be more powerful. But the problem with neomagnets is that they tend to turn into rocks when they're exposed to high temperatures. They lose all their magnetism. So the way manufacturers combat this is they put heavy rare earth elements into the system. Heavy rare earth elements allow the magnet to maintain its magnetism at higher temperatures. So they call this improving the coercivity of the magnet. So really high grades of neomagnets use larger amounts of dysprosium or terbium. The heavy rare earths are way less suitable. So you can see for your electric vehicles, we usually require a very high magnet that will operate at a very high temperature, about 200 degrees Celsius. So these can have something between like 8.5 and 11% of their total grade, or their total concentration will be dysprosium or terbium. And then those used in your wind power generators, what they call SH grade, would use about 4% dysprosium. The overall rare earth balance in the magnet is roughly 30%. The rest of that is made up of iron and boron and other trace things. Well, yeah, your lower grade, low temperature magnets, those used in things like toys, hard disk drives, things that don't get very hot and require operation at very high temperatures. And then as you can see from the map as well, again, over 92% of manufacturing, sintered magnet manufacturing occurs in China. A little bit starting to happen in the US, a little bit in Germany, and some other countries, but most of it overwhelmingly occurs in China. A lot of the Japanese companies hold the patents in these areas too, but still don't produce nearly as much as the Chinese companies. That was kind of an overview of the supply chain. So now I'll talk a bit more about actual material criticality and how rare earths fit into that. I think Lana referenced some of this morning as well. But rare earths essentially are critical. And why are they critical? When we think about critical materials, we usually think of it in these two dimensions: importance to something, and then supply risk. So really like the risk of some kind of supply shock, And then what would the impact of a supply shock be on what other end use? This figure is from a 2008 study that Professor Eggert led, for those of you who know him, bear in mind, by the National Research Council. What's critical depends on your perspective. So the graph that Lana showed this morning was from the USGS. That was really focused on economic vulnerabilities. You could also think about this in terms of risk to decarbonization technologies. You can think about this as risk to your corporate supply chain. You can think about it as importance to a suite of technologies that you're investing in terms of R&D. A lot of different ways to think about material criticality. It's not all just, so when anybody just asks you for the critical materials list or something, you have to really ask what they're talking about. There's not just a list of things that are critical. There's a question that comes up all the time. We'll say, is that a critical material? The question is, critical to what? What are you talking about? It's also dynamic and it changes over time. So what's critical today may not be critical tomorrow. What's critical yesterday, because you care about different things. Demand changes, virus change over time. These are really useful for informing strategy. So like DOE, for example, uses this to inform its investments across the entire critical material space, across different material R&D portfolio. CMI has their own internal critical material criticality assessment that they use to direct their R&D funds. Government uses it to make policy. But they're also used to identify kind of your key raw material risks in any supply chain. I'll talk for a moment about the one that we recently did for the Department of Energy. This one was really focused on overall importance to energy and specifically decarbonization. And as Lana pointed out this morning, rare earths are considered critical elements because they are both high in supply risk and importance to clean energy. But why are they important to energy and why are they high in supply risk? So for the DOE assessment, it's made up of these factors here. It's basically a weighted sum of, or a weighted score based on the different submetrics in the clean energy importance and the supply risk space. Energy demand is relatively self-explanatory, but really this is trying to gauge the overall demand for the products, for the specific materials and energy technologies through 2035 relative to current existing supply, substitutability limitations. What that really means is the ability to substitute individual materials and elements in specific end uses, but also importantly, the ability to substitute components and technologies that use those elements with other things. So when we talk about substitutability, we're not just talking about, can you take this element, put something else in and make it work? We're talking about, can you do something in a totally different way? Can you, instead of using a direct drive turbine, can you use an induction drive turbine that doesn't use any magnets or uses low-grade magnets and just a traditional motor type, for example. Basic availability, now the supply risk, basic availability is really just how much can you get out of the ground within a given time period. Continuing technology demand is the idea that there are other uses of these materials that would continue to crowd out investment and the ability of certain users to get that material because they're willing to pay a higher price. So a classic example of this would be if the Department of Defense wants something and there's only so much of it, they're going to get it. Political, regulatory, and social factors. This is really focused on where things are coming from. What's the risk of a disruption to the supply chains due to some kind of political disagreement, war, social unrest, or really nasty environmental factors, such if one deposit gets as a natural disaster or their environmental permits are revoked, what kind of impact could that potentially have on the market? Codependence in other markets. This is really focused on materials that are mined together. So rare earths are a prime example of this, where your ability to sell or your decision to mine that product is not necessarily just based on the price of that material itself. So a classic example of this would be iridium, which is a platinum group metal, which is totally dependent on the supply and the price of platinum and palladium. The price of platinum and palladium are high enough, you're going to mine your PGM ore, and you're going to end up producing iridium as well. If they're low, you need iridium. Iridium is not going to drive your decision to mine them. The producer diversity is just a measure of market concentration and market power. So kind of simply, if a country basically dominates production of something, then they have the ability to control that market either through producing more, which would cause like low prices, keep other competitors out, or you could just withhold material, cause prices to go up, and keep you from getting what they need. So importantly, we did this for both the short term and medium term. Short term was 2020 to 25, medium term was 2025 to 2035. As the rare earths were relatively high in both of these measures, specifically for their energy demand, very difficult to substitute rare earth elements. And then also producer diversity really plays a pretty heavy role in that as well. So that was just focusing on the raw material side of things, though, right? So that when we talk about material criticality, we're really focusing on that first stage of the supply chain. But we're talking about the resilience of the magnet supply chain. It focuses on all four of those stages that I mentioned before. And so I showed maps that basically showed the same information earlier, but this chart pretty clearly demonstrates as we move from the mining to the separation mining magnet manufacturing stage, becoming increasingly reliant on China for those different pieces, which just means not necessarily bad to work with trade partners and that other countries produce things maybe we didn't want to produce at one point, but certainly it makes it not resilient to potential disruptions and different geopolitical challenges. But things are getting better. So this is a list of all of the domestic projects, not all, this is a non-exhaustive list of domestic projects going on in the US at different stages of the supply chain. So most everybody in the room is probably familiar with MP Materials and the Mountain Pass Mine. So specifically MP Materials is currently mining raw materials from that Mountain Pass mine and concentrating them. And they've also recently begun some level of separation activity as well. But they're an example of an American company that is really focused on trying to develop the entire supply chain all the way through magnet manufacturing. So trying to have a very vertically integrated operation. We have some production of monazite out of Georgia, which then goes to the Energy Fuels. So this project here, Southern Ionic Minerals, produce some monazite from their mineral sands that then gets shipped to this refinery that Energy Fuels operates in Utah, where they do concentrating. Eventually, they're supposed to supposedly do separation and metal refining as well. Why does this work? So one thing I don't remember if we talked about this morning, but monazite has a lot of radioactive material in it, which makes it very difficult to process, especially for normal process, because you have to do something with that waste. The Energy Fuels is a uranium producer, and so they're able to handle that waste. So they're very accustomed to producing radioactive materials and dealing with that, so that makes them kind of an ideal candidate to process things like monazite. So another thing to think about whenever you're reading about a domestic project that's talking about doing something with monazite, separating monazite, you have to ask where they're getting it from and what's the actual product that they're having shipped. And monazite is radioactive material. It's considered some class. I forget what the rating is, but if you ship monazite overseas and you still haven't dealt with your radioactive material at the site, you're now shipping your radioactive material overseas, which drastically increases your cost. So any project that's not talking about dealing with the radioactive material before shipping it, especially on a boat, it'll be pretty hard to make that economic with these under current regulations. Let's see. We also have Phoenix Tailings outside of Massachusetts, in Massachusetts, outside Boston. They're currently producing metal out of mine tailings that exist. And then Novion Magnetics, which used to be called Urban Mining Company, is currently making magnets out of recycled material, I believe from MRI machines one of the risks with making, so there are many different approaches to making magnets from recycled material. One of the ways is just to take what you're given and then make a new magnet out of it. And so one of the downsides of that is, as we discussed earlier, a lot of end uses require specific grades of magnets. You're just having recycled magnets come in. You're making magnets based off of those grades. You don't really get to tailor your magnets to the specific end users that might be most interested in buying magnets. So there are still challenges to overcome, but there's a lot of investment in this area in the US, a lot of companies striving to improve different parts of the supply chain. So there's a lot of focus on the mining side of things. And I guess the point I'm trying to make here is that mining is not really the only problem. In fact, maybe it's not the most pressing problem when it comes to the magnet supply chain. There are bigger challenges in the concept, in the separation, metal refining, maybe the magnet manufacturing space. Let's talk about substitution. So I mentioned before that substitution happens all along the supply chain, not just within a specific application. So why do we care about substitution? Because if you're able to substitute something that would make it less critical, you're obviously able to avoid using things that are difficult to get. So we think about specifically in wind turbines, what we might call element for element substitution would be, as I was talking about before, taking out dysprosium, putting something else in. So instead of using dysprosium, you use terbium. Instead of using rare earths, you use something else. Instead of using the praseodymium, you take some of that out, put some cerium in. That would be element for element substitution. Process for element substitution would do essentially the same thing, but if you're manufacturing something in a different way that allows you to use less of a material, that would also have the same effect, basically. Grade for grade substitution would be something that happens at the component level. So instead of using an N50SH magnet, you'd be able to re-engineer your system a little bit and use something like an N42SH or an N50H, which would operate at a little lower temperature or something like that, but would allow you to substitute the magnet if you couldn't get like a high dysprosium content magnet. Magnet for magnet substitution would be if you were just able to swap out the magnet for different type of magnet together. You realize you didn't actually need a neomagnet in your application. You can do just fine with a samarium cobalt magnet. So there's been a lot of effort in this space targeting what they call gap magnets that are essentially magnets that can fill the need where you don't necessarily need high powered rare earth. System persistent substitution is your most broadest possible form of substitution, which would be substituting out direct drive turbine for induction drive turbine, substituting out a wind turbine for a solar panel, UPS, as broad as you want with that kind of thing. So how do companies actually do this? How did they actually respond? So at the beginning of the talk, I showed that huge price spike. And so what these results show is just basically some questions that were like, well, during that price spike, what did your company actually do? How were you actually able to respond? And so these results are from interviews with actual people at magnet companies and engineers working in the labs that asked how did firms and researchers actually respond to that problem. Turned out process for element substitution was a pretty important approach, and this was due to the development of a technology called grain boundary diffusion technology, which allowed magnet manufacturers to use about 50% less the heavy rare earths, so they were able to decrease their dysprosium and terbium content of their magnets by manufacturing magnets in different ways. This was heavily patented, so it's difficult for a lot of companies to use, but really what the high prices encourages companies to do is find a different way to make their magnets that they could use less material. The other thing they did was not do any kind of substitution, and they just increased the cost to their end user. So you can do that as long as they'll pay the price, right? You can also just absorb your costs, but as I was told by many magnet manufacturers, they're not that profitable to begin with, so that's really what the companies really didn't do that very much. What didn't really happen was the magnet for magnet substitution, and I believe that that was probably due to the fact that it was relatively short-lived. I think if you had a longer time scale and you looked over maybe a 10-year period, you would actually see that there probably was more magnet for magnet substitution occurring, and that, especially with the invention of some of the new magnets that CMI is working on, for example, in the longer horizon, you could see more of that magnet for magnet substitution. So I'll wrap things up. Basically, when we talk about the neodymium iron boron magnet supply chain, it's really characterized by a reliance on the stability of the raw materials market, so the market for earth elements, reliance on foreign countries, in particular China, who dominates really all aspects of the magnet supply chain. And also small pool knowledgeable workers, which I think those of you who were at CMI events yesterday, there was a lot of discussion about that. Intellectual property constraints, which I did not really talk about much today, but this is just the idea that a lot of the patents for these advanced magnet technologies are owned by a small set of companies, and it's very hard to get a license for these companies, for American companies, to produce magnets that way. Extremely large expected increases in demand, especially as we pursue a net zero goal by 2050. And then also just aggressive pursuit of intellectual property by foreign firms that keep American firms from producing things. With that, take any questions.
We have time for a couple of questions for Dr. Smith, if you might have some. Questions for Dr. Smith. Go ahead.
So a lot, like we might see these price shocks in rare earths, but in some cases, the amount of the cost of the end use for them is relatively low, like for cars, for example. So how does that kind of complicate this substitution that we might expect from more traditional markets?
Yeah, that's a good question. So I get at the end of the day, right? That's what you care about. Like, can you sell your car? Can you still sell the car if the price of the magnet goes up? And I guess it would depend on how big the price shock was, right? But there are, so I was talking to Kenna actually yesterday, who's a magnet researcher within CMI. He was telling me about some research where they were looking at a Toyota Prius, and could you actually make Toyota Prius without the use of any magnet at all? Turns out you can't. You have to completely re-engineer the system. You have to use different batteries. You can make it with what they call ferrite magnets, which I didn't talk about much today, but ferrite magnets are permanent magnets made mostly out of iron. But yeah, I mean, you have to re-engineer your whole system. And so you can do it. Like, it's feasible to produce a car without the magnet. And so it just would depend on your cost margin and how long-term, I guess, you think the disruption was going to be if you wanted to avoid it altogether. Hope that answered your question, Bill.
Yeah, let's talk to them.
Any other questions?
Can you just tell us briefly what is the difference between the bonded and sintered magnet? What's the difference between the manufacturing process of bonded and sintered?
I think that will come later, the
Yeah.
difference, but he's asking the cost.
Oh, the cost?
No, not the cost, the manufacturing process. Okay.
Yeah. Sure. I think the short answer is sintered is like alloys that you heat up a lot, and bonded is a powder that you press.
Polygon.
Yeah, they'll talk more about that clearly, but
Thank you.
the markets are totally different. So bonded magnets, we actually do have bonded magnet production in the US. It does not use dysprosium. So those tend to maintain their coercivity at higher temperatures. But they, like I mentioned, they're brittle, more brittle, and they typically are not your higher power, higher strength magnets. So definitely useful, definitely important magnets, an important market, but for the high temperature, especially these energy applications, not usually super relevant, to my knowledge.
I do have a question for you, Braeton. So despite being the part of the same US government, the Geological Survey and the Department of Energy, they have their own list of criticality for different materials. And not only in terms of magnet materials, like rare earth, battery elements, semiconductors, they are pretty different from each other. Why do you think that is?
The short answer is that U.S. Geological Survey looked at economic vulnerability. We looked at importance to clean energy. So when I was talking on this slide about it matters about your perspective, U.S. Geological Survey was using historical data to look at the entire U.S. economy, especially the manufacturing sector. So they were looking at what materials do we need to maintain our manufacturing base in the United States. We were looking at what do we need to achieve climate goals by 2035 using the materials and the technologies that the Department of Energy is currently looking at. So very different perspective. And so when you compare these two lists, you're really comparing apples to oranges. But unfortunately, that's not how policymakers really view things a lot. They see a list, and they see this list, and they make decisions based on that. And sometimes it's difficult to communicate the subtle differences between some of these things. But they have very different purposes. Very different purposes, these two lists.
Yes.
A little beyond the scope of your topic, but I'm curious, can you comment on other rare earths that are used in other use cases like specialty glasses or defense tech? Really vulnerable outside of the current name?
Yeah, I would say specifically your heavy rare earths. So things like europium, gadolinium, they have specialty uses. I think for glass polishing, if I'm not wrong, that's mostly like cerium and things. So cerium, at least colloquially, cerium is kind of known as like this. It's just completely in abundance. There's more of it than we know. That's because it's the first thing you have to pull off, and it's usually actually imposes a cost on your separations process to get to. But there's certainly vulnerabilities in other rare earths as well, just not necessarily for the energy applications.